Staging the 2026 World Cup requires biological perfection. Across 16 stadiums spanning 4 time zones in North America, FIFA mandates absolute surface homogeneity. A soccer ball must roll at the exact same velocity and bounce with the exact same energy return in the humid subtropical zone of Miami as it does in the high-altitude semi-arid basin of Mexico City. Achieving that consistency hits a massive physical barrier. 8 of the designated host venues are multi-use NFL stadiums. These specific arenas were built around permanent artificial turf installed directly over impenetrable concrete slabs. Beyond the floor, the surrounding architecture is intensely hostile to plant life. Massive closed-roof enclosures and multi-ton center-hung screens block natural sunlight and restrict the ambient air movement required to sustain a living biological canopy. Even in venues with translucent ETFE canopies, the roofing materials act as strict filters, stripping away the solar light spectrums turfgrass relies on for photosynthesis. Standard FIFA-compliant soccer pitches combat intense athletic wear through a massive, deep-profile construction. They rely on an active root zone consisting of 12 inches of highly specified sand, resting on top of a 6-inch underlying gravel raft to manage heavy moisture and athletic impact. Bringing that deep-profile standard indoors would require excavating the concrete floors of billion-dollar NFL stadiums to a depth at 18 inches. That level of structural demolition is architecturally impossible and economically unfeasible for a month-long tournament. The engineering mandate was clear. Construct a shallow, temporary biological matrix that behaves exactly like deep earth without tearing into the permanent concrete foundation below. Agronomists at the University of Tennessee and Michigan State University answered this with the shallow profile system, a 16-inch vertical stack designed to sit directly on the concrete. The foundational layer utilizes permavoid units. These 4-inch interlocking plastic modules were originally developed for civil stormwater management. Watch the fluid dynamics. By creating a rigid void above the concrete floor, the permavoid acts as a high-load foundation and a continuous water reservoir. It solves the excavation problem entirely by pulling the drainage system above ground. To manage moisture actively, engineers integrate pneumatic vacuum ventilation lines, like subair systems, into this void. In vacuum mode, massive blowers apply negative pressure to rapidly extract gravitational water downward through the pitch, eliminating surface pooling during heavy rainstorms. By reversing the flow into pressure mode, the same system pumps temperature-controlled fresh air upward. This forces vital oxygen directly into the root system and prevents anaerobic soil decay, while actively heating or cooling the pitch from the bottom up. To separate the voids from the earth above, a highly permeable woven geotextile membrane is laid down as a strict physical filter. It allows water to pass through, preventing the 6 to 10-inch layer of specialized root zone sand from migrating downward and clogging the permavoid cells. Combining lightweight structural lloyds with pneumatic climate control allowed engineers to turn a static concrete slab into an active, fully controllable fluid and temperature reservoir. With the foundation built, the focus shifts to the living canopy. Traditionally, harvesting mature turf requires undercutting, slicing off the lower root system. This induces severe physiological shock in the plant, requiring several weeks of regeneration before the grass can safely support elite athletic play. To bypass that delay, agronomists utilize a cultivation method called sod on plastic. By growing the grass over an impermeable plastic barrier, the vertical root growth is blocked. Forced to sprawl laterally, the roots weave to form a highly tensile fibrous mat. Because this root mass never penetrates deep earth, it isn't sliced. The intact biological carpet is rolled up, shipped, and unrolled onto the stadium's root zone, ready for match play. But natural grass alone cannot survive the extreme biomechanical forces of professional soccer. For temporary stadium conversions, crews deploy a highly specialized in-situ stitching methodology. Needles vertically inject millions of synthetic nylon fibers 18 centimeters deep into the sand root zone. As the grass grows, roots actively wrap around these anchors. The living lateral root web binds permanently to the deep synthetic anchors, creating a hybrid structural composite that withstands rotational shear force from day one. The physical theory is sound, but does a 16-inch stack of plastic, sand, and stitched grass over a concrete floor actually protect an athlete's joints the way 18 inches of native earth does? To quantify safety, researchers rely on the Flex testing machine. This pneumatic rig precisely simulates a player cutting, firing a cleat directly into the turf and accelerating, capturing over 30 distinct ground reaction forces upon impact. A critical metric is rotational resistance. The testing proves that under extreme torque, the cleats safely release from the stitched turf well before the force transfers up the leg and breaches the threshold for ACL or major joint injuries. The data confirmed that a 4-inch layer of empty permavoid modules, topped with shallow sand, absorbs kinetic energy identically to a heavy, conventional deep sand root zone. This specific dampening profile completely eliminated the need for heavy elastomer shock pads beneath the grass. The agronomic engineering successfully decoupled biomechanical shock absorption from physical depth. A natural grass pitch is an intensely fragile biological system, sustainably supporting only 20 to 25 hours of heavy use per week. Navigating this limit requires the engineered system to be installed at extreme speeds, utilizing compact, lightweight machinery that won't exceed the load-bearing limits of the stadium's access tunnels. By utilizing pre-cultivated sod on plastic and modular drainage voids, installation timelines are drastically compressed. A complete stadium field conversion that traditionally requires 13 weeks of steady construction is executed in exactly 3. Once the field is built inside a fully enclosed NFL dome, operators must immediately artificially replicate the sun. Massive LED grow lighting rigs are suspended directly from the high-tension stadium ceilings. They continuously bathe the turf in deeply calibrated pink-hued spectral light, delivering the exact photosynthetic wavelengths grass requires to increase cell wall density, without a single ray of natural sunshine. In northern open-air stadiums facing colder climates, the temperature control goes directly into the soil. Hydronic heating loops are embedded at the subbase level, circulating warm glycol fluid through the profile to keep the soil from freezing and forcefully hold the grass out of winter dormancy. The pitch survives because it operates entirely independent of the stadium architecture wrapping around it. It is a self-sustaining, portable ecosystem. The 5-year research and development program, led by the turfgrass science teams at the University of Tennessee and Michigan State University, solved the central logistical hurdle of the 2026 tournament. The shallow profile system proved so effective that it is actively utilized even in open-air NFL venues like MetLife and NRG Stadium. Crews are burying existing artificial turf infrastructure under specialized sand bases and modular drainage cells, proving that permanent concrete is no longer a barrier to premium biology. This immediate success stands in sharp contrast to the ongoing demands of NFL players, who argue that if stadium owners can rapidly install high-level natural grass pitches for an international soccer tournament, they possess the technology and resources to do so for domestic football. The modular nature of this system means a venue can host a heavy-impact 70,000-person concert on a Friday, clear the concrete floor, roll out the permavoid, lay the intact sod, and deliver a pristine, professional-grade natural pitch within 48 hours. By engineering a way to reliably grow and sustain premium grass inside enclosed concrete structures, this research leaves a definitive blueprint. It proves that safe, high-performance biological sport surfaces can be rapidly deployed exactly where they are needed, regardless of the environment.